Hello my dear students, today we are going to learn oxoacids. Okay, so oxoacids, the compounds which have OH group are called oxoacids. In periodic table, all the elements are not able to form oxoacids. Mainly second, third periods and halogens are able to form oxoacids. So in this lecture, I discuss oxoacids of phosphorus. Oxoacids of sulfur and halogens will be discussed in the next video. So first we learn oxoacids of phosphorus. Oxoacids of phosphorus. Phosphorus forms large number of oxoacids from +1 oxidation state to +5 oxidation state. Now we discuss all the oxoacids formed by phosphorus. First we discuss H3PO2. The name of H3PO2 is hypophosphorus acid. Hypophosphorus acid or phosphinic acid. Phosphinic acid. Next, H3PO3 orthophosphorus acid. Orthophosphorus acid or phosphinic acid. Phosphonic acid. H3PO2 phosphinic acid, H3PO3 orthophosphorus acid or phosphonic acid. Okay, don't be confused with phosphonic and phosphinic. Next, there is another oxide, H3PO4. It is orthophosphoric acid. Orthophosphoric acid. There is no special name for H3PO4. Next, we discuss another acids in which two phosphorus are present. These are H4P2O5, H4P2O6, H4P2O7, H4P2O8. Okay, this one is pyro, this one is hypo, this one is pyro, this one is peroxo. Okay, for your convenience I am writing like this: pyro, hypo, pyro, peroxo. Just increase the number of oxygen by 1. So pyro phosphorus, hypophosphoric, hypophosphoric, pyrophosphoric, pyrophosphoric, peroxo diphosphoric. It is the easiest way to remember all the oxoacids of phosphorus. There is another oxoacid of phosphorus, that is metaphosphoric acid. I discuss metaphosphoric acid after completing their structures. Now we discuss structures of this phosphoric acid. Their structures are very simple. Okay, first we start from H3PO2. The central atom is phosphorus. Okay, first place one double bond, oxygen, one double bond oxygen, first place. And next, see how much oxygens are left. If we place one double bonded oxygen, we will be left with one oxygen, and rest oxygen are OH group. Okay, the remaining oxygen are OH group. In this case, only one oxygen is left, therefore there is only one OH group. Okay, and we have two hydrogen. All the groups you have to arrange in tetrahedral fashion. Okay, because phosphorus is tetrahedrally arranged in oxoacids. In this case, H3PO3, H3PO3, phosphorus, one double bonded oxygen. Next, look at the number of oxygen left. 2 oxygen, so 2 OH bond. So place 2 OH bond, and we will be left with only one hydrogen, this one. Okay, next, here phosphorus, again place double bonded oxygen. Now we are left with 3 oxygen, so 3 OH bond. Okay, next, in this case 2 phosphorus are present. If 2 phosphorus are present, then you have to look at oxygen. If the number of oxygens is odd, then PO-P bond. If number of oxygen is even, then PP bond. Okay, so in this case number of oxygen is odd, therefore POP. One oxygen comes in between 2 phosphorus. If number of oxygens is even, then there is PP bond. In this case, odd number of oxygen, so POP bond. In this case, even number of oxygen, but this structure is different from these compounds. Look at the name of, sorry, the spelling is wrong, phosphoric. In this case, we don't have PP link, as number of oxygens is even, because this compound is peroxodiphosphoric acid, peroxo. In case of peroxo compound, there is always peroxide link. What is the peroxide link? This one. This is the peroxide link, peroxide bond. Okay, peroxide bond. So you must remember the compounds which are named as peroxo, there always be a peroxide bond. So in this compound a peroxide bond is present. Now these two bear phosphorus. Okay, now it is time to place double bonded oxygen. As I told you, each phosphorus bear one double bonded oxygen, so fulfill the requirement. double bonded oxygen. Okay, how much oxygen we already have used? 3 oxygen. Now we are left with 2 oxygen. Out of 5, 3 oxygen already we have placed. Now we are left with 2 more oxygen. So 2 OH bond. Now distribute 2 OH group equally. One is here and one is here. Now we are left with 2 hydrogen. Also distribute equally. 1 hydrogen here, 1 hydrogen here. Next, in this case, again double bonded oxygen, double bonded oxygen. Now we are left with 4 oxygen. That means 2 OH bond. Okay, all the hydrogen have been used. Next, move on to this structure. In this case, the number of oxygen 7. Already we have placed 1 oxygen. Now double bonded oxygen, double bonded oxygen. We already have used 3 oxygen atoms. We are now left with 4 oxygen atoms. So 4 OH bond. Now distribute equally. 2 OH bond here and 2 OH bond here. Okay. Next, in these structures, double bonded oxygen. Okay. Now H4 and oxygen 4. Already we have placed 4 oxygen. So we are left with 4 oxygen atoms. So 4 OH group. Very simple. Just you need to place 1 double bonded oxygen and then look at the number of oxygens left and then connect hydrogen if any hydrogen is left. Next, we discuss about their oxidation state. In this case, if you calculate oxidation state of phosphorus by oxidation rule, you will get +1. Here you get +3. Here you get +5. Here you get how much? 1, 2, 3, 4 +3. Here how much? +5. In this case +5. Now if you apply oxidation rule here, the oxidation state you get would be how much? 8 oxygen -16, 4 hydrogen +4 -16 +4, 4 plus twice x minus 2 into 8. How much? X would be -12 plus 6. Okay, you get +6. But the maximum oxidation state of group 15 elements is +5. They can never show +6, +7, +8 oxidation state. So in this compound we cannot determine the oxidation state by using the rule. It can be determined by drawing the structure. How? Look, in this case phosphorus is forming 5 bonds. 1, 2, 3, 4, 5, and all the 5 bonds are linked to oxygen, which is more electronegative than phosphorus. In this case, all the 5 bonds are with what? Oxygen, which is more electronegative than phosphorus. Therefore, +5. If any atom linked to another atom which is more electronegative, then that element gets +1 for one bond. for 2 bond plus 2, for 3 bond plus 3, depends on the number of bonds linked to the most electronegative element. If the element is less electronegative, then it gets -1 for 1 bond. Look at this. In this case, phosphorus are linked to 2 oxygen by 3 bonds. 1, 2, 3. 2 oxygen by 3 bonds. So plus 3. And 2 hydrogen by 2 bonds. And hydrogen are less electronegative than phosphorus. In this case, hydrogen are less electronegative than phosphorus. Therefore, it gets -2. -2 from hydrogen and +3 from oxygen. So the overall oxidation state is +1. That's why +1. Okay. Now we discuss. Now we discuss basicity. What is basicity? Basicity depends on the OH group. Okay, this OH group. This is called ionizable group. What do you mean by ionizable group? Ionizable group means this group can release H plus ion. That's why it is oxoacid. Ionizable group. That means this group can release H plus. Okay, and this group represents the basicity of a compound. As there are 2 OH groups are present, therefore the basicity of this compound is 2. In case of oxoacid, the basicity depends on the number of OH group. Okay, as this compound has 2 OH group, so basicity is 2. This compound has 1, so basicity 1. This compound has 3 OH group, so basicity is 3. Okay, is it clear? No problem. Next we discuss reducing character. In this case, basicity 2, here basicity 4, basicity 4. Okay, so next we discuss reducing character. Reducing character. Reducing character. Reducing character depends on number of pH bond. Depends on what? Depends on number of pH bonds. Okay, that means more is the pH bond, more is the pH bonds, more is the pH bond, more is the stronger is the reducing character. Stronger is the reducing character. Stronger is the reducing character. Now look at the number of pH bond. In this compound, the number of pH bond 2. Here 1. There is no pH bond in this case. So which one supposed to be more strong reducing agent? This one. This one supposed to be strong reducing agent. Why? Because it has 2 pH bonds. More is the pH bonds, stronger is the reducing character. As it has 2 pH bonds, okay, therefore it is strong reducing agent compared to orthophosphoric acid, which in turn strong reducing agent than orthophosphoric acid. Okay, reducing character decreases in this way. Sometimes examiner asks an example of this. The given example in support of reducing character of H3PO2, phosphoric acid. Very simple example. Simple example, silver nitrate plus H3PO2. It is reducing agent. Reducing agent, it reduces silver. Here the oxidation state of silver is +1 and the oxidation state of phosphorus is also +1. As it is reducing agent, it reduces silver +1 to silver, okay, and itself get oxidized to H3PO4. Okay, what you can see? You can see the phosphorus undergoes oxidation from +1 to +5. Silver undergoes reduction from +1 to 0. So it is reducing agent. How much electrons lost by phosphorus? 4 electrons. How much electrons gained by silver? 1 electron. The loss of electrons by phosphorus put on the side of silver, okay. The gain of electrons by silver put on the side of H3PO2, 1. Don't need to put 1. Now 4 silver, put 4 here. 1 phosphorus, so 1 phosphorus. Don't need to put any value. NO3, it is nitric acid. Okay, I am repeating. Here it is reducing agent. 4 electrons lost by phosphorus. That electrons you have to place before silver nitrate. Okay, the electron gained by silver you have to place before this one, because the electrons lost by this species will be taken by this species. Okay, now balance the species. 4 4 1, so 1. 4 nitrogen, so you have to place 4 here. After doing this, now you calculate the number of oxygens. On the right hand side, the number of oxygens are 12 and 4, 16. On the left hand side, the number of oxygens are 12 plus 2, 14. Here 16 oxygen, here 14 oxygen. 2 oxygen are less on the left hand side. To balance oxygen, we add water molecules. So here we need 2 water molecules. Now this reaction is completely balanced. Okay, this reaction indicates the reducing behavior of H3PO2. Very simple. Next we discuss disproportionation reaction. What do we mean by disproportionation reaction? Suppose a element is in suppose +1 oxidation state. After reaction, suppose it gives 2 products B and C. In B, suppose the compound is AB3, okay. After react, suppose it forms 2 compounds AB2 plus AD, suppose, okay. Now here the oxidation state of A is +1, here suppose +3, here suppose -1. Now you can see this species undergoes reduction as oxidation number decreases from +1 to -1. Also undergoes oxidation as oxidation number increases. Oxidation, here reduction. If any species undergoes oxidation and reduction simultaneously in a reaction, that reaction is called disproportionation reaction. Now H3PO3, not PO2, this compound undergoes disproportionation reaction. The oxidation state of phosphorus is +3. When it is heated, it forms PH3. It is phosphine, and another compound H3PO4. Now here the number of the number of phosphorus 2. So place 2. You will see there is no balance of oxygen because 4 oxygen, here 6 oxygen. Not possible. So place 3. 9 oxygen. You have to place 2 here. 8 oxygen. Again not balance. Now place 4. Here 3 phosphorus plus 1, 4 phosphorus. 12 oxygen. Okay, no problem. This is the disproportionation reaction. Why? Because in this compound the oxidation state of phosphorus is +3. Here it is -3. Here it is +5. So what we can observe? We can observe this compound undergoes oxidation as oxidation number increases, and also undergoes reduction as oxidation number decreases from +3 to -3. Okay, so we can say orthophosphoric acid undergoes disproportionation reaction when it is heated. Okay, last compound we discuss, that is metaphosphoric acid. Very important compound. Metaphosphoric acid. The formula of metaphosphoric acid is SPO3N. Okay, here N can be 2, 3, 4 up to N. Okay, now suppose N equal to 3, the formula would be HPO3. What is the structure of this compound? Very simple. PO, P, 6-membered ring. Okay, in oxoacids of phosphorus, at least one double bonded oxygen and at least one OH bond must be present. In oxoacids of phosphorus, at least one double bonded oxygen and one OH bond must be present. So here also you cannot place another OH bond because phosphorus is already forming 5 bonds with oxygen, and that means what? +5. If you place another OH bond, then this compound would have to form 6 bonds with oxygen, and the oxidation state would be +6, which is not possible because their maximum oxidation state is +5. That's why in metaphosphoric acid the phosphorus always in +5 oxidation state. If the N is large, 4, 5, suppose 6, then what will happen? Then the structure would not be cyclic. If it is 3 or 2, then it is cyclic. If more than 2 and 3, then it is not cyclic. Okay, if n is more than 3, then it will be no longer cyclic, it will be chain like this: phosphorus, oxygen, phosphorus, oxygen, phosphorus, oxygen, phosphorus, oxygen, phosphorus, oxygen, phosphorus, in this way. As you know that the phosphorus contain one double bonded oxygen and at least one wedge bond. So please this is the linear metaphosphoric acid. Okay, so here what you observe, HPO3 link, how much? 3, 1, 2, 3. Here if it is 4, 1, 2, 3, 4, HPO3, that's why it is N. So this is the linear structure of metaphosphoric acid, this is the cyclic structure of metaphosphoric acid. Cyclic structure of metaphosphoric acid is possible up to N equal to 3. If N more than 3, then cyclic structure is not possible, then it will take linear structure, infinite chain structure. Okay, did you get it? All the terms I learned you are given in the NCERT book. Thank you.